Okay, so once again, let me go back. So we are going to look at this topic about text retrieval. In our mind, we should think about that. We have a corpus of documents available. One of the good example is a search engine, because search engine is really a gigantic collection of text documents on the internet. And of course, it employs thousands of crawlers to constantly collect text files from URLs. And then when you want to search for something, you present a query, and that query could be a sentence, or could simply be one keyword or a set of keywords. But no matter what you present, normally it will just, your query will just be taken as a set of keywords. Okay, so even though you enter a sentence. And so that's why we want to look at the mechanisms behind this text retrieval, what kind of models people use, and then eventually we're going to talk about search engine implementation. So first thing first, so we want to look at how we rank documents, right? So you have a queries, I take in the queries, and then which documents I should return, and how we are going to rank these documents to best match the user's interests. Okay, so that's the mechanism we are going to talk about. All right, so first, how do we represent a document, a text document? We know that a text document consists of sentences. Of course, then each document you have paragraphs, you have titles, you have subtitles, you even have publication time or the authors. Sometimes you have the authors, but in general, it is just a sequence of words, right? So using different separations, right? Either separated by paragraphs, sentences, of course, are separated by punctuation, and you organize several sentences into one paragraph, then it's separated by either by the indentation or by empty space, by the empty line. So that is a text document. But for the computer to, when we talk about the retrieval ranking, so what we are really looking at a representation is straightforward. It's just a set. Okay, so you have all these words. We separate these words. Last time we talked about segmentations, right? So for English, it's easy because these words are separated by space, by punctuation. So we collect them, and we don't care about the orders. So there is no order, it's just a bunch of words. But then, of course, in a document, each word or the same word could appear more than once. So then, of course, we need to also count the number of appearances for each word. So then we put these things together into a set, and that is called a bag of word. Right? So the bag of word is just a set of words, okay? But each word could appear more than once, then we also include a word count. So you can think of it as a compressed representation of a multi-set of words. Okay, so a multi-set of words means that you allow the same element to appear more than once. So instead of including each word more than once, I just include a count that indicates the number of times that word appears in the document. Okay, so if you look at this picture, for instance, I have a document D over here, and I have a query. So this is my query. It says presidential campaign news. So it's just a phrase. So what the system will take is to put this thing into a bag of words. So that means now you have 3 words. One is presidential, campaign, and news. So the easiest way to do here is that I will search for document D that contains presidential, that contains campaign, that contains news, as many times as possible, and that D obviously will look like, would better match the query, okay? So that means now we have to first look at frequency, term frequencies. So that's really just a count, okay, word count. So this is word count. But then just looking at the word count is not good enough, because if you have a long document, which of course obviously would have a tendency to include certain word more frequently than a short document. So that means that we also would like to have look at document length so that we can do some kind of normalization. So this is the term frequency is the first thing. And then we look at document length. And the third thing is that since we have a corpus of documents, so we also want to know the number of documents that includes that word. Okay, so that is called document frequency. So that's the third thing. So these things can be done using NLTK or any NLP tools. Okay, so we don't have to do it from scratch. For instance, we can just use NLTK to do that. Okay, so now we are going to look for the first retrieval mechanism that's called vector space retrieval. So the idea here is that we are going to treat a document as a vector, and we're going to treat a query also as a vector. So in other words, what we are, in our mind, what we are thinking here is that we have a vocabulary. So we're going to have a vocab for the underlying document. So let's say this is a V. And then we are going to list all the words in lexicographical order. So then implicitly you have an order. So that means that we can treat it as a vector. Okay, so this order is independent of the word appearances in a document. It's just an order for vocab. For instance, the easiest ordering is use dictionary order, or we call it lexicographical order. So we can just say this is the word. Let's say n is the total number of words in your vocab. So you look at your dictionary. So of course this number is not a small number. It's a huge number. Okay, so on the other hand, if you have a corpus of documents, let's say you have a Wikipedia dump, and you can run through this Wikipedia dump and look at all the words. Okay, so the total number of different words is n. So we have an order, so then your document D would then be a long vector. Okay, it's really a long vector that for each of these words, if it appears, for instance, if W1 appears, we put it 0. If W2 appears, we put it 0. If it appears, we put it 1. It appears, put it 1. If it doesn't appear, we put it 0. So then you see that you have a long vector. And likewise, your query also is the same dimension. So it's a long vector of the same dimension, but of course, obviously it should be shorter than D. So it will only contain small number of ones. The other one is zeros, right? For instance, if W1 appears, it's 1. If W2 doesn't appear, it's a 0. Okay, so that's how we represent a document and a query. So now you have a corpus. Let's say you have a corpus, which means that you have a collection of documents. Let's say you have M documents. Now you are presented with a query queue, and then we're going to compare this query with each of these documents, and then find out, the first thing we want to find out is a similarity. In other words, we want to know which document contains the words in Q the most, right? So that one obviously would look like more similar, would look more similar than the other ones that doesn't even include words in Q. So that is the basic thinking here. So for this similarity, okay, so we're trying to do, so this is called the similarity. The easiest measure to do similarity is a dot product, because after we represent this document and query as vectors, okay, so by doing vector, sometimes we put an arrow on top to indicate now it is a vector. Otherwise, it would be a set of words, right? We have, as I said earlier, we have an implicit ordering of words. So you're using that ordering of words or lexicographical order of words, then you do have an order for each document. Now, once again, this order is independent of the order of word appearances in D or in Q. It's just on a fixed order. So then our goal is to see this D whether it contains these words in Q. So the inner product is the obvious choice, right? So you multiply each of these elements, like 1 multiply 1. So that's 1. So that means now I have one match, and then this one, which is zero, that it doesn't match. So in other words, so whatever that's 1 here, you look at with the corresponding coordinate to see whether D also contains that word. So that is dot product. And a simple normalization of dot product is called cosine similarity. Okay, so that's what we're going to see next. All right. So, so the dot product is the straightforward measure. Obviously, that is not the best measure. Actually, that's not a good measure because it does not include term frequencies, right? As earlier mentioned, that we need to look at term frequency. We also need to look at document length, because implicitly dot product does include document length, but we really want to have a specific normalization to go with it. And then we also saying that a word appears in the document more often. So this is another thing I want to mention here. So maybe I want to open up a screen so that when we talk about these directions, then you understand what that really comes from. Let's say I have a collection of documents, right? So you got lots of documents, DM. So that's my collection of documents. And then let's say I have a word. So let's say this word W appears in every document. So if W appears in each document, such as the word D, the word the, or the word a. So because of the grammar thing, so obviously if you have a text document in English, you're going to see the in every document. You're going to see a most likely in every document. So that really tells you, even though this W appears very often in the document, it doesn't really mean much, right? Because it appears in every document. So likewise, even though this isn't, these are called functional words, even though some words is not functional, it's a content word, but it appears in every document. So then, of course, that word doesn't tell us much about this document in order to distinguish them, right? Because our purpose is to select a document that best match the query. So if it appears in every document, so that doesn't really mean much. So instead, if you have a word, let's say I have a W prime, it only appears in the first document and the last document. It doesn't appear in the documents in between the first and the last. Then this W prime would really will really give more information about D1 and DM because it doesn't appear in others. So that means now we would need to look at document frequency. So document frequency means that for each word, how many documents contain that word. And then we want to measure the importance. So that means that we are going to look at a inverse DF. So we're gonna look at inverse document frequency. So or we call it IDF. So that is the idea why we are going to look at inverse or IDF. Okay, so now let's go back to the previous slides. Oops. I gotta go back. Yeah, it is. Okay, so now let's look at improvement in two directions from dot products. Okay, so dot products is not good enough. So how are we going to improve it? So we have two directions. One direction is to obtain better scoring of xi and yi depending on every kinds of relations you can think of, such as semantic similarities of words, syntactics relations of words, right? Or sometimes we call it co-occurrence of words. So that is one way to do it. The other one is we need to come up with a better normalization. So to come up with better scoring, then we look at semantic point of view and syntactical point of view. So one is term frequency. The other one would be the easiest thing to talk about is the inverse document frequency. Okay, so that's I'm listing a few things here. So the first one is look at term frequency. So that's the word count. So this is term frequency. And then the inverse frequency and term frequency are combined together to come up with a measure. And that measure is called TF-IDF. Okay, so once again, I have a collection of documents. I have a word. I want to know a scores for this W, I, and D, how I'm going to measure similarity or measure importance to match these words. So which document matches better in the underlying corpus of documents. Okay, so obviously we do word count, so this is the easiest thing to think of. And then we do a inverse DF. So inverse DF means now this is the bottom here is DF. The inverse means that we put it in the bottom. So on top of it, so you just need to look at how many documents in your corpus. So I'm using capital D here to instead of C. Okay, so this is a collection. So this is a collection of documents. Okay. The reason we put a +1 here, just want to make sure mathematically, when you don't have anything in your document, these logs still mean something, right? So we don't want to say that. So we want to put a +1 here. So normally, when you see some formula, you don't have this +1, but in your textbook we have a +1. So it doesn't make much difference. Okay, so that is TF-IDF measure. Okay, so this is the first meaningful measure we use to look at how relevant a particular word is to a document. Okay, so this is a relevancy or relevance. And then we have other methods. So for instance, we have a small, simple algorithm to identify keywords, and that algorithm is called rake. Okay. And also, when later on we'll talk about page rank to rank pages, web pages. So that ranking of web pages is independent of user queries. Okay, they just say your page is more popular, then you get a higher rank. So this of course you know that it was invented by Google. So it's called page rank, and of course we can use that algorithm to rank words as well. So then that's called text rank. Okay, so these were the earliest. So the earlier two of the earlier measure that performed well, but then we can improve them. So we have another one called SSR. So that's a shorthand for semantic sentence ranking, sentence word ranking. So we can use this. So this was developed by my group. And this is another one is we call it tensor rank. So that's also developed by my group. So these are much better, but to talk about these algorithms, we need more preparations, and hopefully we do have time to go over these two. But at least we will go over these two. Okay, so Maybe some of the PhD students here can talk about this later when we have time. Okay, so that is one direction. It's improve scoring. The other direction is to come up with a better normalization measure. Okay. Are there any questions at this time?
No question.
All right. Okay, so now let's move. Okay, so the most important slide is the previous slide. Now we just get some understanding of this IDF looks like. Okay, so so we look at this function because the inverse document frequency is defined using a logarithmic function. So there's a log d plus 1. So d is the number of documents. So this, of course, has to do with word. So this word appears in how many documents? So this W is in D, and D is the document in the underlying corpus. So this, the bottom here, is the number of documents that contain word W in D. So maybe you could put a D here, right? So that indicates that this IDF is with respect to this corpus. So then this is really a function. So we can look at this function here as log m plus 1 over k. Okay, so let's say k starts from 1 to m. So what it looks like. So it looks like the curve, that means that. So this x-axis is k. So this k indicates how many documents that contain this particular word. So as you can see here, if it only contains one word, okay, the IDF is big. If you contain a lot of words, so in other words, a lot of documents contain this word. So if only one document contains this word in the corpus, obviously you want it to have a larger weight for that word, because that word really means something, because only one document contains it. So that's here. So this is the highest. So gradually, you have more documents contain that word, and of course, the weight of that word is gradually decreased following this curve. Okay, so that's what it is. And gradually, then of course, you just mean nothing eventually, right? So particularly when this and is equal to this, then it becomes 0, right? So that means nothing. So that is just to sort of help us understand what this inverse DF or what this IDF really means. Okay. Now we're going to put them together, put things together. So we're going to put the word counts together. Okay, so this is really, by looking at the word count, this part you can think of as dot product. So we are going to do a dot product. So in other words, each of these xi, let me do this wi here. So each of these xi and yi, we're going to use TF-IDF for each value. Okay, so instead of just counting one, if it appears in the document D, we use its IDF value. So that's xi and yi now. So then it becomes this. Okay, so you will, let me just, for this, we are going to, so erase this. We're going to let xi to be the word count in the query. So this is the word count in a query. And this yi is yi is TF-IDF of W in Word, also in D. So it appears in the query and also in D for the underlying document. So that means now we're going to look at document frequency for this word for the underlying corpus. So that means we count how many documents that contain this word W, and then take the IDF. So there's a log length of D plus 1. Okay, so that is using TF-IDF. So we write it out, that then it becomes this. So it looks like here we just do the word count we do. So this part here, it just looks like a dot product of word counts. And this one, we can think of it as some sort of normalization. Okay, think about that as a sort of a normalization. Okay, so, and then we call it TF transformation, term frequency transformation. So what we are interested in here is that we are going to transform term frequency using a function, and such that this function is less than s when x is equal to 1, and f of x is close to x, and it gradually moves away from x when x is increasing. So what we really want is a picture like this. Okay. This is a term frequency. Well, we transform this term frequency. So this is a term frequency, and we want something that gradually move away from this term. So in other words, when the idea of this is this. So let's say I have a word that appears in this document, but it does not appear in the other documents. So that really means that this word it should be critical word, right? So we just want to find a critical word. So it's a critical. But then you can imagine if this word appears twice, how much weight it's going to add to this word. It may add some more weight, but if this word appears 3 times, then the weight it's going to add is not as much as linear. So this would be just a word count, right? So this word count means that each appearance is counted equally likely. But then in our case, we know that it appears once, appears twice. Of course, it should have about the same count as is the actual count. But then when you have more appearances, the weight of the later appearances should not be just treated as equal as the earlier appearances. So that's what this means. Okay, when you have more, your counts is greater, increased, then it's not going to be exactly the count right here. So it will be gradually move away. Okay, so that indicates that so if you have thousands of appearances and then the weight is not going to be the same as the actual work counts. So that's TF transformation. So you can also think of that as some kind of normalization. Okay, so that is, and it turns out this idea works. Okay, so let me erase. Oops, we're going back. So for instance, we can use a log function. So that's what we saw here. So this is a log 1 plus x, or we can even do this, log 1 plus log 1 plus x. So that's what we are having here. And for text retrieval, this is better function. So this is f of x, which is equal to k plus 1 times x over x plus k. And this is a known, now we have a name to it. This is known as a BM25, and BM is a shorthand for best match, okay? And this 25 is for the value of k, I think. So we're going to see more later. So in other words, now we introduce a new normalization. So that's sort of the idea of this normalization is not to treat each appearance of the same word equally likely, right? So if it appears once, twice, so of course we get more weight to it, and then you appear the third time, the fourth time, so their weight is gradually going down. And so of course we can use this function, we can use that function, and the best for information for text retrieval is this function. And that is, because it's good, so we give a name to it. So that's called BM25, best match 25, in other words. Okay, so now let's look at what this function looks like. All right, so this is the best match 25, BM25 right here. Okay, so for the value of k, so k, when k is equal to 0, of course that curve is like this, and then k is when the you look at different value of k's, then this curve looks like this. So this YTF, I'm sorry, so this TF looks like this. So it moves away from the earlier one, right? So the earlier one is log 1 plus x. So the gap here is bigger. Okay. Now we are going to look at document length normalization. What we looked at earlier is word count normalization. So we don't want to count each appearance equally likely. But now, how about document length normalization? So one normalization technique is which is straightforward. Okay, so just divide. We can simply divide whatever you measure by the size of the document. In other words, by the number of words in that document. But that turns out is not a good normalization for text retrieval. Instead, for each document D, okay, so for each document D here, we look at its length, right? So we get D. Because what we are trying to do is that you are going to have lots of documents. As we said, we have M documents here. So that is the underlying corpus. So in our mind, that the average length of this, okay, so the average document length will just be, you sum all of these up and then divide it by M. Sum them up. So I from 1 to M. So this average document length would, in our mind, would be something that we should return to a particular query. Okay, so that means now we first set out a middle point. So this is the things we want to return a document that has the average length based on a query we received. But then a shorter one, a shorter document should be rewarded because now it contains the keywords. It also contains all this TF-IDF, and then it's shorter. So we should give some award to a shorter document, and we should give some penalty to a longer document. So if a document is longer, we should give it some penalty. So then the way to do this is to come up with this, right? So we use a parameter B. B is from 0 to 1. Okay, so and we are going to use this as the denominator at the bottom. So as you can see here is that we want this B. In other words, if we want, let's say, I have this one at the bottom. So let me put it here. I have this thing at the bottom. I should put a size of D here. Okay, so this will be the size of D, and then this AVDL. Okay, so when this D is longer, okay, so when this D is greater than its average. So that means this part is greater than 1. So this is greater than 1. Okay, I want this penalty, meaning that I want this thing to be greater than 1 also. So then, of course, because this is greater than 1, 1 plus B plus something greater than 1, right? So let's put an epsilon plus 1B. So it is greater than 1. So that means then I have penalty incurred, because at the bottom means that the whole thing is greater than 1. The whole thing will be smaller than whatever on top here. Right? So this is normalization, put it at the bottom. So if a D is exactly equal to AVDL, then this is equal to 1, right? So if D is equal to this, then this bottom is equal to 1. So then there is no penalty, there's no award. And likewise, if D the size of D is less than its average, then this guy here is less than 1. So that means this whole thing is less than 1. So that means then if we put the bottom, the entire thing will be greater than the whatever on top of it. So that means we give some award to it. So that's what this function means. Okay, so I'll fix that. So I will put the size of D here. So that is document length normalization. Now we can put them together to come up with a measure. So this diagram is just the explanation of what I just said. Okay, so as you can see here, that depending on what is the B value is, the smaller B, your punishment and award is smaller. Larger B, your punishment and award will be bigger. Okay, so then of course how to select this B is it will depend on your underlying corpus, and of course to determine the value, the better value of B, you could use machine learning method. For instance, if you have label data, then you can use the label data to sort of adjust this value B. Okay. But then if you look at your textbook, I think the value B is set to be 0.75. Okay, that would be from a lot of experiments that indicates that when B is equal to 0.75, it gives the best value. So then we put these things together, we come up with two similarity measure. And these two are now commonly used in all search engines. Okay, so one is called pivoted length normalization. So as you can see here, that the TF transformation for smoothing or for normalized word counts, it uses this function. Okay, so it uses log 1 plus log 1, then plus the word count. And the normalization, the document normalization, we use what we just mentioned. This is the IDF. So this is the pivoted length normalization. And then we use BM25 function, put them together to normalize the word count as well as the document length normalization. It becomes this. Okay, so it becomes this. And again, this is IDF measure. Okay, so both of these are good. Okay, some people like this, but this is straightforward to use, and this is actually pretty good in performance. So your textbook finally concludes that among all possible smoothing or normalization techniques based on TF-IDF. Now this is a TF-IDF based improvement. You could either use this or you could either use this. So for this, of course, you need to choose B, and for this you need to choose B and K. Okay, so your textbook gives it a value. Let me see whether I can find it. When is B and K values are the best? So B here is, as I said earlier, B here is 1.75. So 1 minus B is 0.25. So that's why it's called BM25. 25, so that's where that 25 comes from. And for this K value, it's equal to 1.2. So you select this, it comes up good for the second method. For the first method, you can put B75. Okay, so that applies to a corpus of documents. In particular, that applies for search engine. So the corpus of documents, it's huge, right? In general, it's really big. So when you have a smaller corpus, then this B value may need to be changed to a smaller value. So that's so of course machine learning can come into play. How we are going to determine the speed. So that means that you need to come up with some kind of label data. Then you can use the label data to train these parameters. So that's Beck's vector space model based on, so this is based on TF-IDF. Based on TF-IDF scoring of words. Okay, and then of course what the things we do here is that instead of directly using TF-IDF, we added, so plus two things. One is TF transformation. So which sort of like a term normalization, if you want to think about that way. So there's a term normalization. So come up with a better scoring for words instead of just treating each occurrence of the same word equally likely. We're going to using a curve so that we are going to put less weight when you have more occurrences of that same word. So that's TF transformation, or you can think of it as a term normalization. The second part is document normalization. So document length normalization. The other one is document length normalization. And the first one we can think of as a term appearance or term count normalization. So you add these two components to TF-IDF in different flavor using different TF transformation and with the same normalization. The same normalization is still the 1 minus B plus B of this, right? So document length normalization. But the term transformation or the term count normalizations are different. You have these two similarity measure. So which means now is this. So let's say you have a queue, right? So user presents this query, which could be a sentence, could be more than one sentence, or could just be one keyword or bunch of keywords, query words. And then you have a lot of documents, and then for each document, you got to compute this thing. Or using this formula, you got to compute this thing. Then what we're going to rank this D based on Q is by looking at its value. So the highest value will put D closer to Q. So that means that if you want to return, let's say 10 documents, then you compute all of these, and then you pick the top 10. You pick the 10 documents with the top 10 similarity scores with Q. So that's how we're going to return these documents to this query. Okay, so this is text retrieval. based on TF-IDF. Okay, so as we said, we have other methods. So we're going to look at rake. Okay, so it's pretty straightforward. So we are not using TF-IDF. So this is not using TF-IDF. So that means that we don't need a corpus. So this doesn't need a corpus. We just look at each document individually. So instead, we are going to look at each document individually and give a score to each word in this document. Okay, so then that's how we score these documents. So what we do here now is a simple algorithm. So we remove stop words from these. Stop words are those functionality words such as a, the, and, or, right? So it doesn't really have much meaning, right? So semantics, it doesn't have much semantics. We think of those as stop words. You compile a long list of stop words for English and for other different languages. For other languages, you will need to come up with a different stop words list. And then we are going to use these stop words to cut your document into fragments, right? So for instance, I have this document. So let me start a new screen here. Okay, so let's say I have a document. So each line here represents a text line. And then I have a list of stop words. This L is a set of stop words. So we use these stop words to cut. So this will be stop word, is stop word. In between, there is no stop word. And then you look, and then the next stop word is here. And then you look, so you continue to look, maybe the next stop word here, next stop word here, maybe next one here. So then you have a lot of small chunks of text without stop words. Okay, so that's the first thing we're gonna get. So get this chunk, and so on. Okay, so stop words, and then we get this chunk. Okay, now from this, we are going to construct and oh, did you see my? Let's go back here. All right. Chat. Okay. And this, okay. So this is the pre-processing, and then we are going to construct. Now pre-processing occurs this part. You can use any NLP tools to do it, such as NLTK that comes with Python. Oh, by the way, writing Python is fairly straightforward if you know how to do interpreters. You just write out commands. You don't really need declare this and declare that, right? So that's very convenient. Just like you do racket. Have you done racket? Or so this is a flavor of Lisp or closure. So these, of course, it's a recursive function. But Python is like closure, but it's just more like C or Java. So instead of writing recursive function, you just write down normal. When I say normal, means that they are sort of like C and Java kind of language. Like you have for loops, you have if and else, that kind of thing. For racket and closure, there's another one. It's called closure. Also flavor of ifs. Everything you do, you have to have a recursive function. But for Python, you don't. But your statements, your instruction could be individual. You just like you don't have to say write a SQL. You have to get a library in. Specifically, you have to declare all the variables, that kind of thing, right? So Python gets rid of those. So it's a quick language, and I like it very much. So NLTK, after you import it, then you can just use it to do, let's say you come up with a list of stop words, and then you just go through all the words, and then you can truncate your sequence of words in the document by looking at these stop words. So that's pre-processing using NLTK. You can do it. Well, the reason I'm saying this is just in case you want to think about a project, and this is something you may want to get started with. All right. So after we have this, so after this pre-processing, then we are going to construct a undirected graph with content words as nodes. So what is content words is just the whatever trunk. Sorry, the removing these stop words, and that's the content words. And then, so inside the trunk, you have this content word, let's say W1, W2, inside one, then you are going to make a connection. Okay, so they are in the same sequence. We call this trunk a same sequence. Okay, so W1, W2, if it's in the same thing, then we're going to connect it. Okay. And that's it. So you have a degree. And then for each graph, we can count the degree of WI for each word WI. And then of course, we normalize it by dividing it by the word count of WI, and that gives my value of YI. Okay, so then I'm just going to do a dot product XI, YI. Or you can, yeah, so then I'm just doing this to return a document. So directly using this may not be very good. So sometimes you need to do a little justification of YI. But nevertheless, this is another way to, in particular, you don't need a corpus of document because TF-IDF really, you do want to have the IDF component. So if you don't have a corpus, then the IDF component is not there. It's not there. And as I said, the text rank We will talk about text rank when we talk about page rank of ranking web pages independently of queries. Okay, so this is where we are going to talk about that when we talk about search engines. That's one of the things that Google is based on. And of course, Google develops other techniques to run PageRank and also run this query retrieval or text retrieval by developing a platform that can handle a lot of queries, distribute those jobs among different machines so you can do it more efficiently. Okay, so they have the concept of Google made a concept of table, and so we're going to talk about that later. And then, as I said, the SSR, actually we call it SWR, semantic word ranking, and SWR is a part of SSR, and TensorRank also we have a word ranking inside TensorRank, developed by our own, so they perform better than TextRank, much better than TextRank. Okay. So now I want to raise this question just in case you want to do a research. Now, project and research sometimes are different, right? So a course project, you can just use, you don't need creativity, you just use existing methods to solve some problems. And research means there's something people don't know yet, so that you need some kind of creativity. So now this would be a good topic. So for these rake text rank, and then we have SWR, we have a TensorRank. So we know that these two perform better than this on sentence ranking. Now again, they don't need a corpus, right? So the good thing about this is they don't need a corpus. So if you have a corpus, in other words, if we want to apply this into text retrieval, that means that you really have a corpus. We know that for when you have a corpus, we can either use BM25 or the pivoted length normalization to compute similarity scores of a document with the query, right? Now, we said that we can come up a different scoring for words. Now, we do have different scoring for words now. But the question remains unknown is whether they will do, so how good they do in text retrieval rather than sentence ranking, compared with BM25 and the pivoted length normalization. Okay, so we don't know. So this remains unknown. And so we can think about that if you want to do a research paper. And the evaluation you can do is to use Wikipedia as your text document, corpus of text documents. And or you can search for some kind of label data for evaluation. So then you just using these methods to come up with scores for each word with the underlying document, and then you compare with the query words to see whether this comes out better. So in a limited application by looking at chat. So which means you got a question. I want a question is a query. Then I want to find out what would be the best match. So one of my PhD students 2 years ago did a research on that, which combines TF-IDF and rake. Right? So of course we do a little justification, then the results are better in that case. But we didn't look at this because 2 years ago we didn't know this yet. So these are new. So this is new. So that is an interesting research paper, and it will get published if this is done. All right. Okay, so that is all I have. I have 1 minute left. Any question?
No question.
No? Okay. All right. Then I'll see you on Wednesday.
Thank you.
Thank you. Yeah, bye-bye.